So now we're getting into pipeline hazards. So what's the general idea of pipelining? Tony, can you turn to your homework real quick? What's the general idea of pipeline that we learned about last lecture? Okay, so why are we doing that? Yeah, that's correct. Improves performance. So what do we, by doing the putting the buffer in between each stage, what are we accomplishing?
You're putting
multiple instructions on it. It's good. It's good that everybody's trying to participate. I'm not going to complain about that. But everybody, look at me. I'm asking questions. Put your pencils down. Pencils down. Pencils down. Pencils down. You can write all this all you want, but if you don't understand what we went over yesterday, it's not going to matter. So what is pipelining? Pipelining, we're putting stages in between each stage, right? But why are we doing this? We're trying to get multiple instructions here at the same time. So here we're having 3 instructions. And we're trying to have, when we use the instruction memory, we fetch the instruction, we're not using that throughout the rest of the single cycle instruction, correct? So if we have a buffer where we have everything go into the instruction decode stage, we can actually fetch another instruction, right? So what are we talking about? I know these are the answers, but what were some of the issues that we said could come up as a result of trying to put 5 instructions in a data path simultaneously?
You're trying to access one that's not being executed.
Access one what? Register. What want registers? What are other things that you can try to access simultaneously? Memory. Memory. So we sound like the worst doo-wop group of all time. So what else could? So that's what we're defining here, and now y'all can start writing. Pipeline hazard, a situation with which the next instruction cannot complete execution 1 clock cycle after the completion of the present instruction. So what does that mean? That means I have some instruction here, right? And it takes 5 stages, right? And then I would have my instruction fetch stage, instruction decode, execute, memory, and write back, which means that if it works, it's going to complete 1 instruction 1 clock cycle after the present instruction. So the next instruction has to do that. So does anybody remember the throughput equation from yesterday about how long it takes for pipeline data path to execute an ideal situation? So the question states for n instructions and k stages, so in MIPS it's 5, but for k instructions, and you have the clock cycle as T of P, what should that throughput equation be? Exactly right. And so this minus 1 here corresponds to that. So the number of instructions plus the number of stages minus 1 times the number of clock cycles is an ideal situation. So now we're getting to these non-ideal situations, right? So this problem here, this will be a relatively big problem on your exam, 7.18. Define pipeline hazard, and then state and define the 3 types of pipeline hazards, and give an example of each. So, situation in which the next instruction cannot complete 1 cycle after the other. Data hazard. Data hazard is an instruction cannot be completed because the needed data to be generated by another instruction in the pipeline is not yet available. And so what we have here is this could be anything. This could be sub. So here we're updating 1, right? So let's say sub, we have 5, 4, and 1, right? So here's what's happening. We get to this stage. We execute the information. We have the value of 1 here, right? So I'm going to zoom in really quick so you guys can see precisely what I'm talking about. So we have the value. So the value of 1, register 1 is calculated and it's put here, right? But if we have this sub 4, 3, and 1, that means I need this value of 1 from the registers, and this is instructions. So that was n by time. So this is, I need them to come out here while simultaneously, and they come out of the register simultaneously while executing the ALU. So on this buffer, I have the value of 1 that I need in the next instruction, right? So it has not been put back into the register. So I'm getting, what am I actually getting out of the registers? What value of 1 am I getting? What's that? The old value. That's it. You're getting the old value out. So you're not having a consistent amount of data. So by looking at this definition, the instruction cannot be cleared because the needed data was updated in the instruction and is not yet available, meaning it's not been put back into the register. And so you can basically say, to answer this question sufficiently on an exam, this would be sufficient. Add, sub, you can do 4 and 3 and 1. But one of these two here has to match this guy, because you know they're adding these two and putting it here. So the value that's being generated by another instruction in the pipeline is not yet available. So if you do those two instructions and draw this out like so, then you're fine. So that the other blue is showing where the data hazards exist. So if you're updating it in the register, if you're trying to use it in the next instruction, you won't have it available either. So structural hazard is when two instructions cannot execute during a resource conflict. Now, you're not going to see these in this MIPS data path. Sorry. And the reason why is because we have separated out instruction memory and data memory. If we didn't, we'd have this really weird issue. So we know the 5 stages: load word, and we're getting a store word here, right? So when we're accessing store word, we're updating our instructions. We're doing a memory read and a memory write. So we go in, we get our information, it takes all 5 cycles, and we're loading information. Simultaneously, we're trying to calculate the store word while also trying to access another value. So if we had to, every single instruction, if this instruction memory and this data memory were combined, so you know, now that you've worked through the code, or at least some of you attempted to on the project, the whole idea of this instruction memory and data memory is that you have a pointer, right? And it has a 32-bit value, and you have a write value, or a read value and a write value. And when it's read, you get that value and you put the output as a 32-bit result. If you're doing this, if both instruction memory and data memory were combined and you're trying to do it simultaneously, what that would mean is if you're trying to do a data memory access, meaning you're loading or storing information, while simultaneously trying to figure out what instruction you need, you have this resource conflict, and it's called a structural hazard. The designers of MIPS got rid of structural hazards by making instruction memory and data memory separate. And so the last one is known as a control hazard. And so this is an issue where the instruction to be fetched is not known. So what happens here? We have a branch instruction first, where I want to branch 28 instructions, right? And so I would want to go all the way down here, but I'm simultaneously I'm still doing all this. So I don't know whether or not I want to branch until we get to the ALU, right? So here I'd be executing 0 and putting it up to the mixing it with the branch equivalent, do the PC plus 4, and add of the immediate value, and it comes back, right? But here's the thing, I don't know that value until this stage, which means I'm already fetching values of the registers to be putting here. So in registers, I'm writing back to the instruction memory in 5 cycles, meaning that I'm actually executing all the values up until here to do this. And by that point, here, I don't know whether or not I'm going to go to add or if I'm going to go to the next instruction, the branch instruction, right? So we're going to be talking about what happens. This is a concept called branch prediction. especially in multi-processing, that becomes very important when you're trying to process multiple threads simultaneously of instructions to do one program, but then you have to worry about why these branch conditions. And what you got to do is you have one thread does a branch, and then another thread is going to execute the values of what you would be doing inside the branch based on if you decided to take the branch, or is branch taken and branch not taken. And then if you find out that you weren't supposed to take the branch, then you just go backwards and do that all. So you're going to be learning about that. And there's an algorithm that deals with all that called Tomasulo's algorithm. So simplest way to do this on an exam is to have some sort of branch. So if I'm going to have one, you could say $3, and then you could have 2, right? And then you go to the next one, 1, 2, or this one, 1. You'd have to have one there and one there. And then you could just say, we don't know whether or not to execute these next 2 instructions or continue that on. As long as what you write in your TGOs and what you write on your exam demonstrates that you understand this whole point of instruction to be fetched as not known, and we have some sort of case where you're executing these instructions while trying to simultaneously figure out if you should be doing them or not. So that's what's known as a control hazard. Okay. All right, so does anybody have any questions on these before we move on? All right. So next section is we had all the what? What's up? Okay, you just turn around. Okay. So the question is, we have all these problems, how do we solve them? And that becomes more hardware. So you have to add in, so it's known as a data forwarding unit, and you have to add in, it's take a fount for this. So the whole idea of data forwarding, actually before we do that, let me go back to the previous stage. So here we were calculating this, actually let me go back to all the way up here to data hazard. So we calculated this value, right? And we have it on the buffer here. And we have this register holding it in memory, and then the next clock cycle happens. And then I'm trying to take the previous value and put it on the register, right? So if I have the value in the data path, but I'm not getting it from the previous buffer, what do you think I could do to solve this problem?
The buffer was just one block of memory.
No, it's not. That's not the right answer. If I wanted this information, but I have, okay, so here, let me see if I can ask this another way. I have my data path here. So let me zoom in on one. So right now we're only going to worry about this thing here, right? So just envision that's the data path. And so what's going to happen is the first instruction, I calculate 1, and I put, note that is new here. And the register at that same cycle puts 1 old here, right? And so at the next clock cycle, what it wants to do is it wants to put this value here, but I have 1 new here physically. So if I have this value here, if I have 2 32-bit values, what could I do to get the value that I want? Yes, I like that answer. And what are my inputs to the multiplexer? Which 32-bit values? This is where engineering comes into play. You guys aspire to be engineers. Let's engineer. I'm sorry, what? And so this comes from here, and we have it go where? So we put a multiplexer here, right? Very good. So we could have it come back here, and we have a mux. So we add another multiplexer to the
database. Now here's the thing. It could be this. It could be add. So let's say we have 1 here and it's 2 and 3, right? And it could be subtract 4, and then we're replacing 1, which is read data 1. What about this? What if I did that? Now I'm putting them in both. So I put a multiplexer here. If I want them both, what do I need to do to the other one? If I'm putting 1 here and 1 here, and I'm having values, the old values come out here, what do I need to do? Another multiplexer. Very good. So you just add another mux. So let me throw this out at you. Add 1 and then the 2 other things, and then subtract, and then there's an instruction where we don't need it. Now let's do sub 4. Let's see, 4, 1, and 1. So here's what's happening. Now I have my value of 1 here that I want between data memory and writing back. And I have old copies of 1 and 1 there. So what do I want to do? What would I want to do in this situation? If I want this value, the value between data memory and write back.
Send it back through the.
There we go. Exactly. And what do I want to do with that?
Put it on a multiplexer.
Very good. Very good. All right. So just add another mux, or you could have a 96 to 32 mux. So we're going to have 2 of those, and this one's going to be called forward A and forward B. Now, here's the interesting thing. When we get to this data forwarding unit, what's going to happen is you're actually going to be forwarding the 5-bit values from the instruction to this data forwarding unit, which is simultaneously going to make the decisions about what those control signals are going to be. So the data forwarding unit is just yet another controller. All right, so yes.
What exactly would control the mux though? So we have the.
You tell me, because I just literally said that.
Okay, so it's the.
Come on, it's right on the tip of your tongue. Someone help them. Forward A and forward B. Yeah.
Okay.
So it's 9:30 in the morning.
Yeah.
So data forwarding. The output of a resource used by an instruction is forwarded to the input of a resource used by another instruction. So that's what you as engineers just designed, this concept of data forwarding. So, but here's the thing. Sometimes it's not possible to forward data, for example, load word or store word. All right, so let's say you have a load word instruction where I'm loading a value from data memory to the register, and I don't have that value until the 4th cycle. But I need to execute on the 3rd cycle the next instruction. So I'd have to wait 1 cycle before I could actually do the instruction. That is known as a pipeline stall. So the whole idea is you're actually telling it to do a no-op, and I'll show you examples of that in a moment. And that's a control unit or compiler that inserts delays or no-op cycles between instructions to prevent pipeline hazards. So typically, in this case, what you're going to want to do, if you have a data forwarding unit, you'd only need to insert stalls when you have load word and then instruction immediately afterwards needs the value. If you don't have the data forwarding unit, and we're going to go over an example question here to talk about the differences, how would you go about doing that? You'd have to insert pipeline stalls until the value were updated in the registers. So. All right, so here is the way this works. Show the instances where data forwarding is required in a pipeline data path with the following instructions. So here, the first thing you want to do when you're not doing an exam is you kind of want to go through these set of instructions and see if you actually need this value, if there are actually hazards here. So what I would do is I circle 2 because that's the first value that I need. And it's updated at the ALU after the 3rd cycle. So it's on the 4th cycle, anything that needs it, it's not there yet. After the 5th cycle, it's updating, but it's not there yet. So anything that's 2 cycles afterwards is not going to be available to me, right? So here, it's on the ALU to the buffer, right? And then the next stage is on the buffer, circumvents the data memory, it's on this buffer. So that's this instruction. So the next instruction is it's on the buffer, gets written back, updates the registers, but it's still not updated. So this value of 2 cannot be needed. But here's the thing. What do you think that we would need this value? Do I need to do data forwarding for these? Has the key question is, has the register been updated?
No.
All right, well, let's check and see. All right, so here we have, this value's been here, and so subtract 2. And by the way, you don't need to do all of this drawing on an exam. It's sufficient just go IM, IF, EXE, DM, and write back. That's fine. So here we have execute. After the execution stage, I need to be able to data forward, correct? So the reason why is because I have not had the opportunity. So I would do, see, this is S2 here. So this is definitely a hazard. So next, I have to worry about this next instruction, right? So here's the thing. Previously it was here. So next cycle, 2 is waiting here, right? So that's going to be hazard. So then we get to this stage here. So it's being written to, we're writing to the register while simultaneously reading from the register. So do you think this is a hazard? Now, if you were a memory designer, you guys are writing code to simulate instruction memory and registers and data memory, is there a way you could get around this? What's that? That's one way to do it. But let's say I don't want to have that delay in performance. Is there a way I can do it?
Forwarding the data.
Okay, well, that's okay. So forwarding data, but let's say forwarding data, but then the problem is if we have a 3rd stage where we're forwarding data, then we make our data forwarding unit bigger. So there might be a way to offset that size without losing performance, without having to insert a stall. You guys are thinking we're on the right path. But if I have the information, so here's the instruction memory now. So I have the instruction memory, right? And I have an instruction, the register, and I want to write to it, and I want to put this value here, right? What could I do? I've said this term before in class. You got write and you got read. And this is the registers. Any ideas? Remember me saying write then read capability of the registers? And the reason we want to do that is because it will eliminate pipelining hazards. So you write to the register first, then read from it. And that's why in these drawings here that they provide in the textbook, they have it broken up into a register where the first half is blue, right? So that means write and then read, and it should take half of a clock cycle for each of those to do. So that's why when now, going back to Amdahl's law all the way back in section 1, when we were deciding the length of the stages, we have to account for all of these things. We have to account for how long does it take to write to a register, and then how long does it take to read from a register. And so typically, you'll either have your data memory or your instruction decode stage be the longest one in the design. And so your longest instruction would be a load word, which is why, if you remember from last class, the load word took the longest time. So what happens is you take the longest one. Remember the definition of pipelining is part of the definition is that the time cycle, just exceeds the longest stage. So you'd have to account for writing, then reading. And that's what your design would be. So here, we write and we read, and then we put it back on. So then that allows us to cut out this hazard here. And the reason why is because by writing and then reading, we're now putting it on the buffer. Before, if we wrote, then we have to wait a cycle and then read, and then we'd have to, as Aaron said, insert a stall. So that's why if you look at these drawings, we have cycles here, cycles here, but not there. So sufficient answer on an exam would be, I would do this, and then go like that. On these type of exams, people always bring in colored pencils, right? Just in case there's others. Sometimes you can write it out, and we can do sub 2, 1, 3, and people will go IF, ID, EM, W. Just anyway, FD, EMW is even simpler. So then here we know 2 is in the next one, so we have FD, EMW, so we have the forwarding there, right? And then FD, EMW, so you have to forward to the ALU, right? And then here for add, FD, here, so right back, forward to the execution. So we're able to do that without inserting any stalls. So, okay, so does that, let me ask a question. Did everything I just say make sense? Everyone is neutral on this question. Is there particularly tired today? You guys have an exam or something? A lot of you guys have an exam this morning? Two this morning? Wow. Two today? 2 yesterday. Oh, okay. But does this make sense? One of you, please not. There we go. Thanks. I got 2. 2 out of 28. Very good. I hope the percentage is better on the quizzes and the exams. Okay, so now this is a really good problem that kind of describes the whole concept of pipelining. So the 2 pipelining questions you will have that big question that I have about define pipelining, then state and define the 3 types and give an example of each. And the second will be something very, very similar to this problem. So, and I think this is a good comprehensive type problem that really summarizes everything to do with pipelining. So, you know what? Everybody pack up your stuff. Everybody pack up your stuff. Everybody pack up stuff. Not a quiz. Everybody pack up stuff. We're going to wake you guys up, give you guys a little treat today. We are going on a field trip. We're going to do pipelining elsewhere. Because somebody has